6 of them. So the order of this group is 6, right? Because there's 6 members, 1, 2, 2, 6, is isomorphic to the direct product, right, of these two groups. Now the order of this one is 2, has 2 elements. The order of this one is 3, has 3 elements. So the order of the direct product will be 2 times 3. The order of this times the order of that. So it's 2 times 3. So this direct product group here has order 6, and so does that. And that's not surprising, right? If two groups, so if this group, this product group, and this group are to be isomorphic, they must have the same order, right? They must have the same number of members. Otherwise, I mean, it's just impossible to have the two group tables the same if the orders of those two groups are different. Right? A 7 by 7 table and a 6 by 6 table doesn't match, doesn't fit. Right? Okay, so you asked to prove that. Okay, quite a few details here, so I'll be glancing at the book quite a lot because quite a few steps. It's a non-trivial example, but it's sort of fairly typical in some ways of this kind of proof. You know, given two groups, prove that they are isomorphic. All right. Well, your first step is to you got to find a mapping. Right? You need to find an F and show that it makes sense. That you're mapping some element from here into an element here, and you have to show that that mapping makes sense. That what you get is suitable to the problem. That's a little vague. I'll explain in concrete terms in a minute. Okay, so our first step is find an F. Find a mapping from this to this. Now, an F. Maybe I'll go down here. Hope you can see this. Okay. So let's take an element of this set. So I'm going to call it just a general element. It'll be one of these. So A here, it's just an integer. This A would be either 0 or 1, 4 or 5. Okay? So and it's mod 6. Right? So let's assume this maps into this. Now this is a direct product, right? Now the elements of a direct product take this form. Right? So this is an element from Z2, and this is an element from Z3. So now, and these elements are residue classes. Okay? So what's a general element of this group? So so we're proposing mapping an element of this into one of the elements of this. So here's our suggestion. It'll be A2, A3. Okay, so of this form. Okay? When you take a direct product of two sets, in this case two groups, because it's a direct product rather than a Cartesian product. Remember the difference? Cartesian product's more for in the context of sets, and direct product is when you're talking about groups. So the direct product is the Cartesian product of groups. Right? Just a question of terminology. All right, so that's our proposition. That's what we suggest that the mapping F should be of this form. Okay, because these are elements. These are groups. Right? This is one group, another group. And these two are also groups. So these are elements. Now, does that make sense? Now, this letter here, this number, can be 0, 1, 2, 3, 4, or 5. Right? And this number can be 0 or 1, and this number here, oops, sorry, it should be here. This number can be 0, 1, or 2. Well, if now this number here could also be, and let's say it's naught, but it could also be plus or minus 6, or plus or minus 12, or plus or minus 18, and so on. So say we have a different number here. Like this could be plus or minus 6 or plus or minus 12. So this number here is said to be a representative of the residue class. Now, typically you choose the smallest one in a sense, now speaking, because it goes on plus infinity into minus infinity. So choose a value, its smallest absolute value, if you like. That's the usual way. That's the usual representative you use. But this there are other numbers. So if you had this, if these are the same, that means A and B are congruent, right? So that implies that A is congruent to B, not 6. Okay? So in other words, A minus B is divisible. Well, let's say 6 divides, divs A minus B. Right? If A and B are congruent, mod something, mod 6, then A minus B can be divided by 6. Okay? So 6 divs or divides A minus B. All right? Okay, so if I now here's where the notion of well-formed comes in. If I put a B here such that A and B are congruent, mod 6, will I get a B here? Does it make sense? Like so question. Yeah. So if I choose a number here that's congruent to A, let's call it B. So A and B are congruent. So I put a B in here. Like instead of having 0, I could have plus or minus 6, or I could have plus or minus 12, or any of those numbers. Okay. So if I put that number, that alternative number B in here, will I get BB here? Will I get this? Will I get that? That's the question. So what I need to prove now is that if I put a B in here, where A and B are congruent mod 6, will I get this? Now if I do, then this suggestion, this mapping, this F of this giving me this, that's my proposition. Then if I put a B in here, instead of getting A here, I get this. If I get that, then my F is said to be well formed. It makes sense. Like if this here is different from this, then I'm in trouble, right? It would not make sense. It would not be well formed. So what I need to do now is actually prove that this F is well formed. In other words, I need to show that this, with the number A here, is the same as this with the B. Now A and B are congruent mod 6, but are they congruent mod 2? Are they congruent mod 3? You're probably sensing what the proof's going to be from what I just said, but okay. All right, well let's try and prove that. So if this equals that, then this suggested mapping is well formed. Makes sense. Well, so let's try to prove that. And then once it's well formed, then we have to show that this F here is bijective, and then we have to show this. Right? So quite a few steps in proving that two groups are isomorphic. All right, let's see. So okay, so Now we've used this second number and we've said it's congruent to A. So B is congruent to A. That's what this means. Okay? That means, that's the definition of congruency, if you remember. It means that the mod, whatever it is, in this case it's 6, divides into A minus B. So 6 divides A minus B. That implies, if you think about it, 3 divides A minus B. If 6 divides A minus B, so does 3, obviously. Right? And it also implies 2 divides A minus B. Okay? If you can divide an integer by 6, that means you can divide it by 3 and you can divide it by 2. Yes? Right. Well, if these two things are true, you can conclude that A is congruent to B mod 3. And from this one, you can conclude that A is congruent to B mod 2. Mod 2. Alright? Now if that's true, just keep deducing. So that means that this residue class of A mod 2 includes B, right? So you could rewrite this just